Hello everyone, my name is Shue. I come from Worcester Polytechnic Institute. Today I'm going to introduce our work, Avoiding VPN Bottlenecks, Exploring Network-Level Client Identity Validation Options. VPN is used by a lot of enterprises to connect their remote users to their enterprise networks. It comes with some benefits that's why people use it. First of all, it can protect the data confidentiality and authenticity. Secondly, it helps with traffic management. For example, an enterprise will not allow its employees to watch Netflix when they are working. The third one is it can simplify the access control. However, VPN also comes with some drawbacks. The first one could be the bottleneck. There are some enterprises that deploy a dedicated VPN server, which is not like a professional VPN gateway. Which can achieve LAN rate VPN bandwidth. The second one is VPN adds on redundant encryption upon HTTPS, which is already used a lot in our network activities. The third one is a lot of enterprises, they deploy a third-party VPN service, which could be very expensive. With this discussion, we know that VPN has some redundant functionalities and drawbacks, except it can simplify the access control. So we really want to explore a method that can help with the authentication without those redundant functionalities. Or this work contributes in certain ways. First of all, we design and implement a dynamic identifier insertion system upon the software-defined networking technology. It can help with the enterprise application servers to authenticate a remote user. We also provide with open source IP tables module that can help organizations to easily deploy our system. Before introducing our method, let's go through some background knowledge. IP addresses was originally designed for recognizing a remote user. However, IPv4 addresses has already run out, and people invented the carrier green net to help with the transition from IPv4 to IPv6. However, there are some features come with CGN. First of all, it will assign each host private IP addresses instead of public IP addresses. And it will cause one public IPv4 address be shared by a lot of more users. And that one IP address could change a lot to one specific user. That makes the enterprise network very hard to recognize a remote user from just the IP address. There are at least 92% of cellular networks already deployed CGNs, and 5G network which is part of cellular network, also will serve the more residential networks. That means the residential networks are also going to be affected by CGN. There are researchers trying to split the locator and identifier functionalities from IP addresses. So there are some works like HEAP and Muse. However, all of those methods require to modify the intermediate network infrastructure, so they come with deployability issues. In our work, we are trying to deliver or identify information inside the IP in IP packet. So IP in IP is already standardized, and we will use the outer IP header for routing a packet, and the inner IP header is used for delivering or identifying information. So because it's already standardized, we believe that the intermediate network will not drop it. Our system is designed to help with organization networks to recognize an individual user, even though they share IP addresses with others, or they have very dynamic public IP addresses. So our system is more like providing with first-pass authentication information that can help with organizations with authentication. The robust authentication is left to application layer. So our system is designed to defend on the side attackers instead of the on-pass attackers. Our system is designed for any Kerberos-like system. The reason we do that is because most of the companies they use Kerberos because they use Active Directory, which is provided by Microsoft. There are two parts of our system. One is a key transfer, another one is a key verification. However, before that, each client needs to indicate its support of our protocol. So when the user sends out an authentication request, the first packet is going to be elevated to the SDN controller. The SDN controller is able to encapsulate the packet into an IP packet, and then it sends out the packet. When the authentication server receives it, it learns that the client supports our protocol. Then it generates a client key and inserts into the IP packet and send it out. When the controller receives the backward packet, it can decapsulate it, it can extract the client key and store it into its local database. So when the client subsequently send out a request to the associated application server, controller is able to detect it and it can encapsulate, it can craft another IP packet and insert the associated client key into the packet and send out to the application server. The application server can further detect this packet and extract the client key and verify the client key. It will allow the request if the client key is valid. We have implemented our system in a local area network plus a remote controller. So this is to simulate the network propagation. Inside the local area network, we have a laptop to simulate the client machine. We have a TP-Link router flashed with OpenWRT and Open vSwitch used for the SDN agent. We have another laptop run two virtual machines, one for the authentication server and one for the application server. The first of all, we evaluated our effectiveness. So we have tried to let the client authenticate with different situations, with no token, with invalid token, with a valid token. And the result shows that only users with provide with valid tokens can access the remote network, the application server. Next, we evaluated how much time that our system adds to the original system. The green line shows the round-trip time from the network to the controller, and the blue line shows that network runs with an idle SDN controller, which means without our system. But the right line shows the round-trip time with our implementation. The results shows that our system adds like 3 to 10 milliseconds to the original system without any SDN stuffs. But it also shows that our system adds around like 1 to 3 milliseconds to an original SDN architecture. And because our system only works on the first packet, we believe that this delay is not going to be perceived by the users. We also evaluate the performance when we move the SDN agent from the physical router to the unhosted device. We do this because we believe that this can be another using scenario of our system. According to the two figures, we can see that the blue line stands for the SDN architecture itself. It adds only up to 1 milliseconds to the original round-trip time, which is shown by the green line on the figures. The full implementation of our system, shown by the right line on the figures, only adds up to 3 milliseconds to the original round-trip time. So we can see that having the SDN agent on the unhosted device outperforms the SDN agent on the physical router. We have such result because usually an unhosted device has more computation resources than the physical router. We also evaluate how bandwidth can benefit from our system. We simulate the enterprise network setup, which has a VPN service running on a general-purpose server rather than a dedicated VPN hardware. The bandwidth is evaluated by clients downloading large files from a web server. We vary the number of clients from 1 to 5 to show the bottlenecks. On the figure, we use a black line to show the baseline performance, where clients directly download files from the server. It shows the largest bandwidth in all situations. Then we use a green line to show that there is a network gateway which runs no VPN, and the blue line, there is a VPN service running on the proxy. As a result, we found that for our architecture, when we put the SDN agent on an host device, shown by the red line, it improves IPsec bandwidth 2.5 to 2.9 times, only decreases the baseline performance 1 to 8%. However, shown by the green line, the throughput is much lower because of the limited computation resource of the physical router. As I mentioned before, our system just provides information for a first-pass authentication. The robust authentication, like username and password, is left for application layer. And also we sacrifice the defense for the on-pass attackers. It may also raise some privacy concerns. To conclude our work, we have identified that VPN can have some redundant functionalities that we may not need today. We want to remove them and achieve some simplified access control. So we come up with a Kerberos-like system to help organization networks to accurately authenticate end users, even though the end users can share public IP addresses with others. We also implemented open source IP tables module for reference for organizations to easily deploy our system. For the evaluation part, we found that our system can effectively enhance the bandwidth bottlenecks for enterprise networks, while introducing small network latency to network clients. That's it for my talk. Thank you very much for listening.